Today we will talk about binomial distribution. Binomial distribution is a discrete variable distribution. So variable x follows binomial distribution with parameters n and p. So we'll talk about what is this variable x and what kind of variable follows this kind of a distribution and what this distribution looks like. So remember, distributions are for the population always, right? So this is a discrete variable, discrete random variable, where there's a finite number of trials and each trial has only two possible outcomes, and these trials must be independent and the probability of success in each trial must be the same. So probably that makes no sense to you right now. So let's talk about variable x. Is a discrete variable. So let's say we're talking about we toss a coin, a fair coin, ten times. Okay, so finite number of times we are tossing it, so the number of trials is finite, and it's a fair coin, and we want to know what is the probability of getting exactly 4 heads. A fair coin is tossed 10 times. How many heads can we get? That would be our variable x, right? So x is number of heads in this case, right? How many heads can we get? If we're tossing a coin 10 times, we can get x can be equal to 0, no heads, very unlikely but possible. 1 head, 2 heads, 3 heads, all the way up to 10 heads. We cannot get more than 10 heads if we are tossing the coin only 10 times. So the values of x can be 0 to 10. That is the sample space for x, right? So you notice that these are discrete values, so this variable x is a discrete variable. Okay, now what we are seeing is that in each toss, what are we looking for? Was it a head or not? Was it heads or not? Every toss, so we are tossing 10 times. In each trial, do we have only 2 possible outcomes? So we are tossing 1 time. Either the outcome is a success or a failure. Success is when we get heads, because we want to count how many heads we get. So that's our successes in a trial. Did we get head? Yes, then it's a success. No, that means it's a failure. So there are only 2 possible outcomes. Either it is success or it is a failure. Either it is a head or it is not heads. Okay. We don't care what else happens. We are only wanting to know if head occurs or not in each trial. Okay, so that means in each trial there are only 2 possible outcomes. Either head or not heads. These are the only 2 possible outcomes, heads or not heads. Now, are these trials independent? That's another condition that must be met. These are independent tosses. What you get on the first toss has no impact on what you get on the second or third or subsequent tosses. These are independent tosses. So yes, these are independent trials. Then we are looking for, is the probability of success the same in each trial? We are told it is a fair coin. So probability that once in your first toss you get a head is 0.5, right? probability that you get a head in the second toss is also 0.5, and the same for all the 10 tosses. So in each toss, the probability of success is the same, which is 0.5. It doesn't have to be 0.5, it could be 0.2 or whatever, but it is the same in each trial. Okay, that is what is important. Probability of success is given by P, and probability of failure is 1 minus P. So if success occurs, let's say its probability is 0.5. If what is the probability that success doesn't occur? 1 minus 0.5, that would be 0.5. So that is given by Q, or you can say 1 minus P is equal to Q. So if a variable meets all these conditions, and I'll repeat, it's a discrete variable. There is finite number of trials. So we are not saying we are tossing a coin repeatedly until we get 4 heads. We are saying we'll toss a coin certain number of trials with times, that is 10 times. So that's a finite number. So it's a finite number of trials. In each trial, there are only 2 possible outcomes, success or failure. And the probability of success in each trial is the same, and all the trials are independent of one another. If all these conditions are met, then it is this variable x, which is a discrete variable, will follow a binomial distribution, right? So if it follows a binomial distribution, then we say x follows binomial distribution with parameters np. In our example, x follows binomial distribution with sample size 10. We have 10 trials, and probability of success, that is heads, is 0.5 in each trial. So that's how we'd write it. These are the parameters of a binomial distribution, n and p. N is sample size or number of trials, and p is the probability of success in each trial. So I've just explained this, what is written here. Now what I want you to do is read each situation, each question. There are 8 different questions posed here. In each question, you have to identify if the variable x will follow binomial distribution or not, or whatever variable name is, x or y, if that variable will follow binomial distribution or not. So read this one first and try to think if this variable will follow binomial distribution or not. You may pause the video at this time so that you don't see the solution until you try it yourself. Okay, so pause. Now once you have tried, now let's look at it. A bag has 15 red and 35 blue balls. 6 balls are drawn with replacement. So how many balls there are in total? 50. What is the probability that a ball that is drawn is red? Is 15 over 50. That is 0.3. Correct? Now, what is the probability that it is a blue ball? That is 35 over 50, 0.7. Okay. Now we are saying that 6 balls are drawn randomly with replacement. It means we are putting the ball back. Because we are doing it with replacement, these 6 balls are drawn independently. They're not dependent on one another. The probability is not impacted by what you got on the first row. Okay, so in each, now we are told x is number of red balls. So we are drawing n is equal to 6, and x is number of red balls. We can get 0, 1, 2, 3, 4, 5, 6 red balls, right? All possible. So this is a discrete variable. In each trial, the probability of red is 0.3. So P is 0.3. Q is 1 minus 0.3 is equal to 0.7. Okay. So we're not interested in blue balls, we're interested only in red. So I've erased the blue one. Now, they're independent because it's with replacement. The probability of success remains the same in each trial because we're putting the balls back as we are drawing them. There's finite number of trials, 6, right? So all the conditions are met. Excuse me. So all the conditions are met. Therefore, this variable x follows binomial distribution with n 6 and p 0.3. Similarly, try the next one. Take a couple of minutes, pause the video, and then check this one. If you've tried it, then you can look at this explanation. What is given to us is there are 1,500 balls. Out of these are blue, red, and green. There are marbles. 7 marbles are drawn with replacement, so we are replacing it. That means they're independent draws. X is number of red marbles. So that means how many red marbles can we get? X is equal to 0, 1, 2, 3, 4, 5, 6, 7. Not more than 7 because we are drawing 7 marbles. So 0 to 7, anything. Discrete variable. Independent because it's with replacement. Number of trials is n is equal to 7, so finite. Now, is probability of success the same in each trial? Are there only 2 possible outcomes in each trial? So we are interested in red marbles. So we have to ask question, is it red in each trial? The question that we are asking is, the marble that we just drew, is it red or not? That's it. We don't care what other color it is. So that means either it is a success. Success means red marble drawn. Failure, not red drawn. Okay, so only 2 possible outcomes. And then probability of success is the same because it's with replacement. So probability of success is 200 divided by 1,500. You can do the math. So all conditions are met. Therefore, X follows binomial distribution with N 7 and P, whatever it is, 200 divided by 1,500. Try the next one. Pause the video, try it, and then watch it again. A bag contains 500 blue, 200 red, and 800 green marbles. 7 marbles are drawn randomly. It doesn't say with replacement, so we'll assume that it is not with replacement. X is number of red marbles drawn. So either it is red or not red. So only 2 possible outcomes. X can be 0, 1, 2, 3, 4, 5, 6, 7. So discrete variable, but without replacement. That means the trials are not independent. The probability of success is not going to be the same in each trial, and therefore this variable X will not follow binomial distribution. Let's try the next one. Again, pause the video, try this first, and then check the solution. A researcher is collecting data from 1,000 Binomial families. X is number of families that have children. The question the researcher is asking each family is, are there children in your family or not? Either there are or there are not. So only 2 possible outcomes, right? N is equal to 1,000. These are 1,000 random families, let's say. So they're independent. Let's say, it's not given, but let's say 80% families in Winnipeg have children. Let's assume. That means if we select a family randomly, what is the probability that family has children? Is 0.8. That means probability of success is 0.8. Okay. How many families might have children out of 1,000? 0, 1, 2, 3, all the way up to 1,000. So discrete, right? So all the conditions are met. the probability of success is 0.8, same in all the families. So that is X follows binomial distribution with n 1000, and if P was given, then 0.8. But it was not given in the original question, which is okay. The X will still follow binomial distribution. Pause the video, try the next one. Now a researcher is doing a survey and is asking 1000 Winnipeg families how many females are there in their family. X is number of females in the sample. So the question they're asking is how many females are there in their family. So their n is equal to 1000. In each trial, the number of possible outcomes can be infinite, because they can say there are 0 females in the family, or 1, 2, 3. So in each trial, the number of possible outcomes is not just 2 success or failure. They're not saying yes or no. They're saying maybe there are 3 females in a family, or 5 females, or 1,000,000 females in a family, right? So even though n is finite, in each trial, the answer is not yes or no. It is instead certain number, which can be any. Okay, so that's why this will not follow binomial distribution. Read the next one. Pause the video, read the next one. A dentist evaluates a person's 32 teeth. X is number of teeth that have cavities. So n is equal to 32. And the dentist is asking a question for each tooth. Is there a cavity or not? Okay, so that he can count how many teeth have cavities. So X is either 0 teeth have cavity, or 1 or 2, or all the way up to 32. Correct. In each cavity, in each trial, that is in each tooth, the question is either it has a cavity or it doesn't. Right? So that means only 2 possible outcomes in each trial or each tooth. Now the question is the probability of success would be having a cavity in each tooth, is probability of success the same in each trial? Now think about your teeth. You see that your teeth have different shapes. The back teeth are flat and they have grooves in them. They're wider, so food accumulates, can get stuck in there more easily, and the cavities typically occur in the back teeth. So the probability of cavity occurring in the back teeth is much higher than probability of cavity occurring in the front teeth, right? Because of the shape of the teeth. So the probability of success is not the same. In each tooth. Probability of cavity is not the same in each tooth. Also, these teeth are not independent. If a tooth has a cavity, it's an infection that spreads to the next tooth. It's more likely to happen to these teeth than a tooth that is on the other side of the mouth, for example. If there's no cavity on that side, then this tooth will have much lower probability of having a cavity than this tooth, because this is just beside an infected tooth. So the probability of success is not the same, and these teeth are not independent with respect to cavities. So X will not follow binomial distribution. Take a moment and read the next one. Pause the video, read the next one, and try to attempt it yourself. X is number of students who own a car. So how many students can own a car out of 50? 0, 1, 2, all the way up to 50, discrete variable. For each student, what is the question being asked? Do you own a car or not? So either yes or no. That means 2 possible outcomes in each trial. Okay, probability of success would be the same again. If 15% students own a car, then probability of success is 0.15, right? So that would be the same, given or not, would be the same for all the students. Then the independent, these are randomly selected students, so they're independent, and so all the conditions apply. X follows binomial distribution with n 50, and p, if it was given, then it is 0.15, or maybe it is not given, so we don't know the p. Okay, pause the video, try the next one. There are 2 variables, x and y. For each of them, tell me if each of them follows binomial distribution or not. So two bags, A and B, have balls. 2 balls are drawn, 1 from each bag. It doesn't say with replacement, so that's not with replacement. But the balls are being drawn from 2 separate bags, 1 each, right? So they're independent bags. Bag A has these balls and bag B has these balls. X is number of red balls. Will the variable x follow binomial distribution? What we have is 2 balls are drawn. Either it is red or it is not. So only 2 possible outcomes. N is equal to 2. 2 possible outcomes in each trial. Independent because they're 2 separate bags. So even if we did not put the first ball back into the first bag, we're not drawing the second ball from the first bag, we're drawing it from the second bag. So it doesn't impact. So independent. Now, is the probability of success the same in each trial? The first bag, A, probability of red is 5/20, or sorry, 10/20. Probability of red in bag B is 5/20. So the probability of success is not the same in both the trials, the 2 trials, right? So X will not follow binomial distribution. How about Y? Again, we're drawing 2 balls, but we're asking how many, Y is number of blue balls. Now all these conditions are the same. N is equal to 2, the only 2 possible outcomes, it's blue or it's not blue in each trial. Probability of blue in bag A is 5/20, and probability of blue in bag B is also 5/20, right? So that means probability of success is also the same in each trial. Y will follow binomial distribution with n2, and probability of success is 5/20, whatever that is. Okay, so if you suspect if a variable follows binomial distribution or not, you can check these properties and determine if the variable will follow binomial distribution or not. So if a variable follows binomial distribution, its parameters are n and p, which I've already talked about. The mean of binomial distribution is given by mu x. So instead of just calling it mu, we are calling it mu x so that we can distinguish it from normal distribution. Simple formula, mu x is equal to np. If you know n and p, then you can calculate np. The standard deviation of binomial distribution is given by sigma x, okay, which is equal to square root of npq. If you were to find variance, that would be npq, or np times 1 minus p, right? Q is 1 minus p. So that is simple. Now what does this distribution look like? This distribution is not always symmetrical. It is symmetrical only when probability of success in each trial is 0.5. If it is less than 0.5, it is skewed to the right. If it is greater than 0.5, it is skewed to the left. And you notice that it is not a shaded area like we had in binomial normal distribution. Instead, these are discrete bars, right? You see these bars are discrete bars, there's gap in between them. So these distributions are not always symmetrical. They're symmetrical only when probability of success in each trial is 0.5. If it is less than 0.5, skewed to the right. If more than 0.5 for probability of success, then it is skewed to the left. Now, what do we do with these distributions? If it is variable x follows binomial distribution, we can find the probability of certain number of successes. For example, if we toss a coin 10 times and we want to know what is the probability of getting exactly 4 heads, if the coin is fair coin, then what we want to know, let's say, and I'm just gonna make up this example, we toss a coin, let's say a fair coin is tossed, let's say 6 times. What is the probability of getting exactly 2 heads? Not less, not more, exactly 2 heads. That's what we want to know. First of all, you can see that this variable x follows binomial distribution. So x follows binomial distribution with n is 6 times, and probability of success, because it's a fair coin, so probability of head is 0.5, so p is 0.5. Now the question is asked, what is the probability that we get exactly 2 heads? So x is equal to 2. This is what we want to find out. In binomial distribution, we can actually find this out. Remember, in normal distribution, this would have been 0. But in binomial distribution, we can actually find out what is the probability of getting exact numbers of successes. So for that, we will use a formula that is called the binomial formula. Some of you might have seen this formula before. This is the binomial formula. So what is this formula? Probability x is equal to k is equal to n choose k times p raised to power k times q raised to power n minus k. What does that really mean? And this is coming from this. If you know factorials, what we have here is number of combinations we can get exact number of successes. Okay, so and we have a function for this part of the formula that is called NCR. So what we are finding out here is, let me make it less messy. Our question was, where did the question go? Here. A fair coin is tossed 6 times, right? This is what the question was asked. What is the probability of getting exact 2 successes? The exact number of successes that we want to find the probability of is called K. So how many successes are we interested in? Exactly 2. That means K is equal to 2. And our formula is probability x is equal to K, which is 2, is equal to n choose K times p raised to power k times q raised to power n minus k. That's the formula. It's coming from this formula. So we have a function in our calculator. What we are doing is we are saying if we have total n number of trials, what is the probability of getting exactly k number of successes? Okay, how many ways can we get this? For example, if you are tossing a coin 6 times and you're interested in exactly 2 heads, maybe the first 2 are heads. So you toss the coin 6 times. Okay, maybe this was head and this was head and these were all tails. This is one way you can get head. Remember, we made a probability distribution table last time where we were putting all these kind of combinations. Or maybe it's possible we get this one head, then we get tail, then we get head. Rest all our tail. Or maybe we get head, tail, tail, head, tail, tail, and so on. There can be so many different combinations. We may get tail, head, head, tail, 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 right? So it could be so many different combinations. How many such combinations can be formed? That is n choose k, or this part of the formula, factorial n divided by n minus k factorial times k factorial. Okay, that's how you find the combinations. Now on your calculators you have to, so let's first write what is n. N is 6, k is 2, times p is 0.5 because it's a fair coin, raised to power k is 2, times q is 1 minus 0.5, raised to power n is 6 minus k is 2. So this is basically talking about, this is basically taking into account number of successes, probability of success raised to power number of successes, times probability of failure raised to power number of failures we are interested in. So we have 2 successes but 4 failures out of 6, right? That's what we are interested in. So how do you do this? This is n6 choose 2. So in your calculator type in 6 and then NCR. Now you may have to press shift before you press NCR depending upon where your NCR is. Then press 2, then times, P is 0.5, so put it in bracket, raised to power 2, times Q is 0.5, bracket, raised to power 4, equals. If you do this, you'll find the probability of getting exactly 2 heads if the coin is tossed. A fair coin is tossed 4 times. So I'll do this math and you also try. I'm getting 0.234375. You getting the same number? If you did only this part, 6 NCR2, 6 NCR2 equals, if you did that, there are 15 such combinations. We are making these combinations, there are 15 such combinations. You can check if you just do this part or only this part, equals. Okay, so but if you do the entire formula, then you should get this answer. That is the probability of getting exactly 2 heads when a fair coin is tossed 6 times. Now what I want you to do is try the next question, read it and try the next question. Actually, before we do this, I want you to practice this formula a lot. So what I want you to do is, let's add another sheet if there isn't already. We'll see why the shape of binomial distribution is not always symmetrical. We'll check that. So let's use a few questions. I'll type so that it's less messy. So a fair coin is tossed six times. X is equal to number of heads we get. Construct probability distribution table for the variable X. So what is this variable X? It is number of heads. How many heads can we get if we're tossing a coin six times? So the sample space for X will be 0, 1, 2, 3, 4, 5, 6. If we can calculate probability of 0 successes, 1 success, 2 success, and so on, then we can construct this probability distribution table. So probability X is equal to 0 is equal to n choose k, n is 6, success is 0, times p raised to power 0, p is 0.5 because it's a fair coin. Let me erase this. N is 6 minus 0 is 6 equals, calculate that. Get 0.015625. That means probability of getting 0 successes is 0.015625. Similarly, find it for 1 success. 6 choose 1 times 0.5 power 1 times 0.5 power 6 minus 1, that is 5, is equal to 0.09375. So 0.09375. Similarly, we can find it for 2 successes, which we already did, I think, earlier. So I'm gonna just use that. Oh, I wish I hadn't erased this. Okay. Point 234,375. So you're just putting the value of k is different. Similarly, we can find this. 6 choose 3 times 0.5 power 3 times 0.5 power 3 equals 0.2945. Similarly, X is equal to 4 is 6 choose 4 times 0.5 raised to power 4 times 0.5 raised to power 6 minus 2, that is, 6 minus 4, that is 2, equals, let's do this quickly. Point 234,375. If you do it for X is equal to 5, again 6 choose 5 times 0.5 raised to power 5 times 0.5 raised to power 1, and this comes out to be 0.09375. And for 6, probability X is equal to 6 choose 6 times 0.5 raised to power 6 times 0.5 raised to power 0, which comes out to be 0.01562. So now if you construct a probability distribution, you have constructed a probability distribution table. Now if you construct the distribution itself, this is the variable X. X can be 0, 1, 2, 3, 4, 5, 6. These are the possible values of X, right? So on this axis, what do we have? We have the probability or relative frequency we called in different distribution. So the highest I need is 0.29, the lowest I need is 0.015. So I'm gonna say no, this is 2. Okay, that's better. So we can just draw these bars. This 0 is 0.01562. So that would be this tall. Then we have 0.09. That's about this tall. Right? Then 0.2343. So maybe that's about this tall. Then we have 2945. So that's probably this tall. And we have this, then we have this, and we have this. So you see it is symmetrical. Here it was a fair coin, P is equal to 0.5, so we get symmetrical distribution. What I want you to do is try the same question. I'm going to copy this question. I'm going to paste it here. What happened? It didn't paste. Okay. Let's say it is not a fair coin. Now I've changed it to from fair coin to probability of head being 0.3, which is less than 0.5. I want you to do exactly the same thing as we did before and then construct a probability distribution table. Okay, so take a few minutes. This will give you practice on that formula, and then you'll notice that this distribution looks more like this. So it's not symmetrical. Okay, then so try this. X is 0, 1, 2, 3, 4, 5, 6, and find the probabilities using the binomial formula. Then again, I want you to try the third one. So here probability of heads is, let's say, 0.7. Again, do the same stuff. And you will notice the distribution looks something like this. So again, it's not symmetrical. This is when probability of success is greater than 0.5. This is skewed to the left, 0.5, and probability of success is less than 0.5. It's skewed to the right. It peaks on the left hand side. Okay, I'm gonna break right now, and then in the next part of the video I'll go with it. So if you have tried calculating these, I got these numbers for when probability of head is 0.3. So the numbers I got, the curve would look skewed to the right. And when the probability of head is 0.7, the distribution looks skewed to the left. Okay, so that's where we know that the distribution is symmetrical only when the probability of head is, or the probability of success is 0.5. Okay, so hopefully you got enough practice on this formula, binomial formula. So if you can quickly do these questions, this question on page number 4. I've already done part A for you. Try to figure out, look at part A and then figure out part B, C, and D. So for part B, the question is, what is the probability that at least one ball is blue? That means 1, 2, 3, 4, or 5 balls are blue. That means the number of successes we are interested in are 1, 2, 3, 4, 5. Okay. Now we can calculate the probabilities of each one of these using the binomial formula and add them all up, because it's OR and they're mutually exclusive, right? So we can do that, but there's a faster way to do it. What is the sample space for this variable? 0, 1, 2, 3, 4, 5. We know the probability of the sample space is equal to 1. That means probability x is equal to 0 plus probability x is equal to 1 plus probability x is equal to 2 plus probability x is equal to 3 this must all be equal to 1. Correct? We know this much. And our question is asking probability x is equal to 1 plus probability x is equal to 2. This is the question we are asked, right? Now, we can see that this one is what we want to find out. So if we can take this onto the other side, what do we get? Probability x is equal to 1 plus probability x is equal to 2. This pink portion must be equal to 1 minus probability x is equal to 0. So you can calculate the probability of x is equal to 0 and subtract that from 1. And I'm not sure if I'm right, but I'm getting 0.598. That's what I'm getting. So what I did, 1 minus probability x is equal to 0 is what I did, which is 1 minus, using the binomial formula, n is 5, right? Yeah. Choose 0 times probability of blue ball is 10 over 30. So okay, I used the wrong probability. So that's not the correct answer. Raised to the power 0 times 0.67 raised to the power 5. So what does that come out to be? Let me do it again. So that is 1 minus 0.1350, which is equal to 0.865. If I've done the math right, this is what our answer is. Okay, hopefully you feel comfortable with this formula. Part C, more than 4 blue balls. I'm going to make some space here. So n is equal to 5, p is equal to 0.33, k is more than 4, so k is 5, that's it, right? Because we are drawing total 5 balls, more than 4 would be 5. It's not at least 4, so if it was at least 4, then you'll say 4 or 5, but it is more than 4, so it is only 5. So we get 0.0039135. You can keep just 4 decimal places, you don't have to keep more than that. Okay, part D, no more than 3 green balls. No more than means this much or less than this. So K would be 0, 1, 2, 3. P is green ball. There are 5 green balls. N is equal to 5. So P is 0.1667. So I'm not going to do this math, but probability X is equal to 0 plus probability X is equal to 1 plus probability X is equal to 2 plus probability x is equal to 3. Or you could do 4 and 5 and then subtract that from 1. So do this and yeah, that would be your answer. Another question, let's look at this. Read this question, do part A and B. This is what I'm getting. Check your answer. Part B, student gets at least 25 out of 50 questions right. That means K is 25, 26, 50. Now have fun. Right? That's a lot of K values. Well, how do we do this? For that, we'll have to learn a theorem. Okay. Sorry about that. Let's talk about a law of large numbers. What does this law state? As the sample size gets larger, as the n gets larger, the binomial distribution gets more and more symmetrical. It appears more and more symmetrical. So, for example, if p is 0.25 and n is 5, then it's a pretty small sample size. The distribution would look something like this, right? Skewed to the right because p is less than 0.5. Now, if your sample size was instead of 5, it was 25, you would notice that this distribution looks more crowded and a little bit more symmetrical. If your sample size increased to 100, then you'll have 101 bars here. They'll be very tightly packed. And then this tail is so low that it almost doesn't matter. So this portion looks pretty symmetrical. So this tail gets thinner and thinner. So based on this, a theorem has been proven, which is the central limit theorem. What does this theorem state? It states that when n is large enough, the binomial distribution behaves approximately normally. So it looks like a normal distribution. Remember what is normal distribution? Normal distribution is a symmetrical distribution with shaded area. In binomial distribution, we don't have shaded area. Instead, we have bars. But when the sample size is large enough, we'll talk about what is large enough, such that there are so many tiny little bars here. Even though these are discrete bars, they look so packed together that it looks like a shaded area. And then this tail is so low on this. Yes, there is a long tail, but the values on that tail are almost 0, very low. So if you look at only this portion looks symmetrical and shaded. And so this is almost like a normal distribution. So that is the theorem that has been proven that when sample size is large enough, the binomial distribution behaves approximately normal. It is not a normal distribution, it is still a binomial distribution, but it behaves like a normal distribution if sample size is large enough. What does sample size large enough mean? Large enough sample, how large is this large enough sample size? When NP is greater than or equal to 10 and NQ is also greater than or equal to 10, then we can assume that X is approximately normally distributed. Binomial variable X is approximately normal. It is not normal, it is still a binomial distribution, but it looks like a normal distribution. A third condition is when N is very, very large. What is N? Population size. Populations are typically very, very large. Okay, so we don't have to really worry about that. As long as NP and NQ both are greater than or equal to 10, then we can say our sample size is large enough to assume that a binomial distribution behaves approximately normal. If a distribution behaves like a normal distribution, then we can use the standard normal table to find areas on this distribution, right? So let's see with our example, we wanted to know what is the property X is greater than or equal to 50 where N was 50, right? So there were so many K values. So what do we want to do? We will first check, is NP greater than or equal to 10? Is NQ also greater than or equal to 10? If this is true, then we'll say the central limit theorem applies. NP is, N is 50, P is 0.25, so this is 12.5. So yes, it is greater than 10. NQ is equal to 50 times 0.75, that is 37.5, which is definitely greater than 10. So both NP and NQ are large, and our 50 questions could be coming from an infinite pool of questions. So now, what do we do now? We conclude that the central limit theorem, CLT, central limit theorem, applies. If this theorem applies, that means we are saying our distribution looks like a normal distribution. Even though it is not a normal distribution, it looks like a normal distribution. Can we find the mean of this distribution? Of course we can. Mu x is NP, sigma x is NPQ divided square root. So we have looked at these formulas before, we have not really used them, but these are the mean and standard deviation of binomial distribution. So can we find mean? Mean is NP, which is 12.5. Our question was X is greater than or equal to 25. So 25 would be somewhere here on this curve. More than this. This is the area we want to find out. Because it's approximately normal, we can convert this into Z. Z is equal to 25 here. Z is equal to X minus mu over sigma. So mu X, sigma X. X is 25, mu X is 12.5. Sigma X is square root of 50 times 0.25 times 0.75 square root. So let's do this math. So we get 25 minus 12.5, which is 12.5 divided by 3.0618. You're getting the same value. So Z comes out to be 4.08. So Z at this point is 4.08. What is the area on its right hand side? Hopefully you remember how to find this area. You know that the largest Z value we have is 3.49. Area on the left hand side of that is 0.9998. So area on its right hand side is 1 minus 0.9998, which is 0.002. If area on the right hand side of 3.49 is 0.0002, then what is the area on the right hand side of if we go further to 4, area on the right hand side of that would be almost 0, right? So that's what we can write here, that area is 0 approximately. Anything that we calculate based on central limit theorem that makes this distribution approximately normal, the probabilities calculated based on that would be approximate probabilities, because we're using approximate normal distribution. So probability x is greater than or equal to 25 is approximately 0. So what I'm trying to say is that if you don't prepare for a test, the probability that you pass a test with 50 questions, multiple choice questions, just by guessing, the probability of passing is 0. So that is binomial distribution. Now, an extension of binomial distribution is sample proportion distribution. What is this distribution? In this, we are talking about sample proportions. So first, let's talk about proportions. This is how we would find proportion of successes. That is number of successes divided by total number of trials, right? So let's say if a coin is tossed 200 times and lands heads 80 times, what proportion of the trials did we get heads? So that would be, we got heads 80 times out of 200 trials. So that is 0.4. Correct? That is proportion. Now, we are talking about a sample of 200. This would be sample proportion, right? So, sample proportion is given by symbol p hat. Very important to recognize this. But population proportion is p. P is probability of success. For example, if I say that a fair coin is tossed 200 times, what is the probability of success, a probability of head on that coin for every trial? It is 0.5 because it's a fair coin. So if we somehow toss the coin millions of times to get all the population of tosses, then almost 50% times it would land on heads, right? So that is the population probability. That's the probability of something, success. probability of something happening, that is P, that is population proportion. Okay, so you understand what is proportion. We can calculate sample proportion if we have certain number of tosses, and in that we are counting the successes, then number of successes divided by total number of tosses. But if we are given the probability of success, then that is population proportion. So let's look at this example. This sample proportion distribution, what do we have here is a distribution is of sample proportions. Okay, it may look like this if sample is large enough. So what is this distribution? Its mean is P, which is population proportion. Or probability of success. Its standard deviation is square root of P times 1 minus P over N. Okay, this distribution, its mean and standard deviation are P and square root of P times 1 minus P over N. The symbols are not in your notes, so I'm going to write these symbols for you here. Mu, mean of this distribution, its symbol is mu P hat. Standard deviation of this distribution is given by sigma P hat, just so that we know which standard deviation we are talking about. Okay, so let's look at an example to understand this distribution. As long as you understand sample proportion and population proportion, this is really easy. So let's say I hit this question now. It's too old, but it's no longer funny. Let's say 65% Americans say that Donald Trump is unfit to be the President of the United States, POTUS. So we are saying 65% Americans say that he is unfit. That is the population of America saying. That means population proportion is 0.65. Then a random sample of 1,000 Americans is asked if Trump is unfit to be POTUS. Now we're talking about sample. If a sentence is talking about sample, everything in that sentence is about the sample. So n is equal to 1,000. And what is the we want to know what is the probability that in the sample at least 60% say that he's unfit to be the president. So what is the probability that at least 60% in the sample, right? So sample proportion is greater than equal to 60%, that is 0.6. This is what we want to find out. Okay. So how do we find that out? Again, because sample size is large enough, it is 1,000, which is very large sample size. We can assume approximate normal distribution. The mean of this distribution is mu P hat, which is equal to P, which is equal to 0.67. Now sample proportion we are interested in, our variable here is sample proportion, remember that. So sample proportion we're interested in is 0.6. That would be somewhere here. At least means this is the area we are interested in. So if we can convert this 0.6 into Z, because it's an approximate normal distribution, Z will be equal to P hat. Our variable is changed now. It is not X, it is P hat minus mu P hat over sigma P hat. So which will be equal to P hat we are interested in is 0.6 minus P mu P hat, which is P, which is 0.67 divided by square root of P times 1 minus P over N. So 0.67 times 0.33 over 1,000 square root of that. Let's do the math to find Z. So we get 0.07 divided by 0.0149. Comes out to be negative 4.70. I'm not familiar with this answer, but probably it is correct. Check if my math is right. So we want to find the area on its right hand side. The area on its right hand side would be, everything will be on its right hand side, right? So 100% probability that at least 60% Americans in the sample of 1000 would say that he's unfit, if in the population 67% say that he's unfit. Try part B. Probability p hat is less than equal to 0.67. I know where I made a mistake. P was 0.65. I was reading 0.67. Let me just correct this. So we get Z equals negative 3.32 maybe. So area on its right hand side, we can check up the table. Negative 3.32. Area on its right hand side would be 0.9994. Or no, 3.32 or 9995. That would be the answer. Part B was a probability that in a sample of 1000, at no more than 67% say that he's unfit. So that's what we need to find out. Again, let's draw. This is what we need to find out. Convert this into Z. Let's do this. So we get 1.33, and we want to find area on its left hand side. Point 9082. Or whatever that is. That is your answer for part B. So why don't you try the remaining questions? And I'll give you the answers. So I'm going to pause the video. You also pause it and then show you. So here are the solutions for these questions. The first one I'm getting 0.729. The second one I'm getting 0.184. Then the next one I'm getting 0.9131. Check. The next one is 0.1736, the right hand side area, and the last one I'm getting this, which is approximately equal to 0.